Today, I will be explaining epistasis using fire-breathing dragons and the color of fire that they breathe. Obviously, these are fictitious creatures, but they can be used to explain epistasis in a way that all people can understand. Epistasis occurs when the genotype of one gene covers up the expression of another gene. I will be discussing one part of epistasis called single recessive epistasis. We will look first at a normal dihybrid cross so we can get an understanding of what would happen with no epistasis. This Punnett square shows the genotypes of the offspring and the color of fire the produced dragons will be able to breathe. Between a cross of these two heterozygous dragons, the resulting offspring would have a phenotypic ratio of 9 to 3 to 3 to 1. But when there is single recessive epistasis, what actually happens is that no purple fire-breathing dragon will be produced because these two little A's are epistatic to the B locus, meaning anytime there are two little A's, the orange fire-breathing dragon will always be produced, regardless of what is occurring at this B locus. So, the four genotypes of a normal dihybrid cross would look like this, with this ratio, but when there is single recessive epistasis, these two genotypes would actually both code for the orange fire-breathing phenotype. So, looking at the Punnett square for single recessive epistasis, we can see that this occurring here, instead of having a 9 to 3 to 3 to 1 phenotypic ratio, we actually have a 9 to 3 to 4, because these little recessive A's always results in the orange fire-breathing dragon. I like to think of epistasis in a pathway that I will explain using keys and doors. If you are a dragon with the big A in your genotype, you have a key to the first door and can go through to breathe green fire. If you don't have a big A and instead have two little A's, you do not have the key to the first door and cannot breathe green fire. If you can make it through the first door and breathe green fire, you might then be able to go through door 2 and breathe blue fire. To do this, you must have the key, which is the big B seen here. If you have the big B, you can go through door 2 and reach the end product, which is the blue fire-breathing phenotype. If you instead have two little B's, you will not have the key to door 2 and will be stuck behind door 1 as a green fire-breathing intermediate. Looking at a more normal-looking pathway, we can see the precursor phase, which is orange fire breath in this case, the intermediate phase, which is green fire breath, and the end product, which is blue fire breath, and the pathways to get to them that we just talked about. Looking back at a Punnett square example, it will hopefully be easier now to understand how epistasis affects the ratios of phenotypes. This example is a cross between a dragon with a big A and two big B's, and a dragon with two little A's and a big B. The Punnett square shows the resulting offspring, with half of the offspring possessing the genotype that codes for the blue fire-breathing phenotype, and the other half the orange fire-breathing phenotype. These have a big A with no double little B's, so they have the blue phenotype. These all have two little A's, so they are stuck at the precursor phase and have the orange fire phenotype. The resulting phenotypic ratio is 1 to 1 because we have 8 that breathe blue fire and 8 orange fire. And looking at the four genotypes expected from a dihybrid cross, we see that only this one and this one are present due to single recessive epistasis, which explains why only the blue and orange fire-breathing phenotypes are seen. Here are the external sources I used for my video.